This is an overview and demonstration of the progress made on my relay computer up to April 2016. Now, if this is the first you've ever heard of my relay computer, then please do visit my website at relaycomputer.blogspot.co.uk where there's plenty more information about this computer. So, for the first time in my videos, I'm going to introduce the graphic you see before you, which basically shows what progress has been made so far on the relay computer. The bits that are completed are shown in green, and the bits that haven't been started yet are shown in red. On the left-hand side is a diagram of the computer's architecture. This is covered in more detail on my blog, but effectively here it shows that registers A, B, C and D, along with the ALU and 3 condition registers, are all complete. As you can see, there's many registers outstanding, and we're currently without memory or program counter and incrementer. The diagram at the upper right shows the completion status of the physical cards in each of the 4 bays W, X, Y and Z. Currently all 5 cards in the Z bay are complete, which are the AD register, BC register and the 3 cards that make up the ALU, control, arithmetic and logic. Lastly, at the bottom right is a list of the completed instruction classes. At the moment, that's all red, as the cards built so far have been operated manually rather than orchestrated via an instruction. That's soon about to change though. At the moment, this diagram is showing the computer as of the last full demonstration video I did, back in August 2014. How time flies. Since then I've been busy, not just on this computer, getting it to the state where we can run ALU, SETAB and MOV-8 instructions. This should make the computer a little more interesting to watch, although note, it'll still only be 1 instruction at a time until the memory, program counter and incrementer are constructed. So, if I now update this diagram, firstly there's a new instruction register, highlighted in the architecture diagram on the left and also as a new card in the X bay at the right. This holds the current instruction code to be performed. There's also 5 new cards in the W bay, although these are shown in orange as they're only partially completed. Just enough for the 3 new instruction classes shown bottom right. The first 2 cards jointly form the sequencer, the next 2 cards form the control, and finally the last card is a decoder. Okay, so with the progress diagram out of the way, let's have a quick overview of the computer as it currently stands. So, welcome to my relay computer. This is a picture taken face on. And if you see something odd going on in the bottom half of the computer, that's me laid on the floor taking the picture. Hi! Clearly I haven't quite got the gist of studio photography yet. Anyhow, if I rotate the computer clockwise, here's the view from the right, back and left. And yes, I am aware there's a mess of cables coming out the back. These are all temporary just to get the computer working as it stands. Eventually these will all be nice and neat, and more importantly within the confines of the computer case. Speaking of the case, you probably guessed that that's also a half-finished job. Mainly to ease working on the insides for now, but eventually it'll be encased in black perspex so that it'll look a little bit like this. Both the front and rear covers are removable. I'll show that now. If we take a closer look now at the front and rear, you can see that the enclosure is broadly split into 2 halves, the upper and lower enclosure. Focusing on the upper enclosure, we can see that it's broken into 3 sections. At the bottom are the primary switches, which is the main way that the computer is operated. These are accessible even when the front door is on the computer. At the top left, when viewed from the front, is display A. This shows which control lines are currently being operated by the computer, but also allows the user to directly operate these control lines for debugging and testing purposes. Alongside this is display B, which shows things like the status of condition registers, current instruction code and class, ALU operation, data bus value, and finally the amount of juice the computer is consuming. Here's a close-up of the upper enclosure. And here's it seen from behind. The lower enclosure is split into 4 bays which will take 5 cards each. Viewed from the front and going clockwise, the bays are named W, X, Y and Z. The cards are designed such that any Z card could fit anywhere in the Z bay, but a Z card couldn't be used in the Y bay. This is because each bay has unique connectors for each of the card types. Let's take a closer look now at each of those bays, and I'll go in alphabetical order, starting with bay W. First up is a sequencer, which is spread across 2 cards due to the number of relays and connections required. The diagram on the right shows what each of the card's LEDs actually mean. And note that the grey dots signify where future LEDs will be placed as the card gains more functionality. For now though, we can see the 9 states of the FSM on the left and the derived sequencer pulses C, D and E on the right. Next is a controller, again made up of 2 cards, and finally the decoder at the bottom as a single card. The decoder takes the current value in the instruction register and decides which instruction class that represents. The controller takes the current instruction class and operates the right control lines at the right time according to the sequencer pulses. Moving on to the next bay, bay X, we find the instruction register. I'm not going to go into too much detail on each of these cards, as you're probably already bored enough, and needless to say, you can find out more info on my blog. Yes, I will keep plugging it. The next bay is bay Y. There's nothing in there yet, so let's go on to the next bay, which is bay Z. This is the one and only bay that has a full set of fully completed cards. The first 2 implement the registers A, B, C and D. Now, in case you're wondering what's going on the right hand side of the AD register card, just near the LEDs, see that strip of white? That is a legend strip on each card, just in front of the LEDs, and on this card it never seems to want to stay stuck down. Eventually, when I've built my 3D printer, yet another project I've got on the go, I'll make some plastic clip-on strips so you can see the legend from the front of the card. The 3 remaining cards make up the ALU: Control, Arithmetic and Logic. Again, if you want a bit more detail on these, you know where to look. URL in the video description below, please thanks. Right, so that's pretty much it for the overview. So let's move on to actually getting the computer to do something interesting. Well, I say interesting, it depends on your point of view I guess, but if you persevered this far then I assume you are interested in what I'm doing. So here we go. So basically this is the same example I've used in previous demonstration videos, but the difference this time is rather than operating the control lines directly, we'll give the computer individual instructions to perform that will do the job for us, one step nearer to a real computer. The example I'm using is a relatively simple calculation of 2 plus 4 plus 1, all times by 3, and then with 3 subtracted. Now, although this could probably come across a little banal, this actually gives us an excellent opportunity to demonstrate the 3 new instruction classes. First job then is to add 2 and 4 together to get 6. Now, I'm writing this program in an assembly language using mnemonics that I've specifically chosen for this computer. Now this will all mean nothing to the computer itself of course, but I'll take you through how we convert this into instruction codes in a bit. Now, using the architecture diagram at the right, we can see that we need to load a 2 and a 4 into the ALU so that you can add them together. Now that's easy enough to begin with, as we can use the load immediate command to stick a value of 2 into the B register. However, the computer can't stick values in any old register, only the A and B registers. This means we have a bit more work to do. We load a value of 4 into the A register and then use the move instruction to copy it to the C register. Yes, it'll copy the value even though the instruction is called move. Don't ask. Move is what everyone calls it. With the right values in the right registers, we can now ask the ALU to add those values together. Now the ALU can place a result in either the A or D register, and if we don't specify either, it'll assume we want the A register. Following these 4 instructions, the A register would now contain a value of 6. Moving on, we now want to add 1 to the 6 we've got so far. The quickest way of doing this is to copy the 6 into register B and then increment it back into register A. Increment only takes the value in the B register, ignoring any value in register C. With these 2 instructions, we'd now have 7 in register A. We now need to multiply the value we've accumulated in register A by 3. However, this computer doesn't know how to do multiplication because it's architected with a reduced instruction set, or RISC for short. This means less wiring and relays, but does mean more work when we're programming. No matter, we can do multiplication by repeated addition, which is what we do here by sticking the accumulated 7 in both B and C registers, then adding, copying A to B, and then adding again. The expected result of 21 can then be found in register A. Last step then is to take 3 from the 21 to get 18. Now those who have read up on the instructions set on my blog will know we can take a shortcut here and load an immediate value of -3. But I wanted to show using the ALU a little bit more, so I'm actually going to load +3 into the B register and then negate it by performing a 2's complement. Effectively, a logical NOT followed by adding 1 via an increment. This gives a 2-bit representation and -3. With -3 and 21 in registers B and C respectively, we can add to subtract, as it were. Once the program's finished, register A will contain the value of 18 that we're aiming for. So now we've written this program, what do we do with it? Pull out suggestions only, please. The assembly language we've used here is designed so it's just about human readable, whilst being tightly coupled to the instructions available in the computer. We need to convert each line to an instruction code that the computer can understand, a process known as assembling. We're going to do this by hand here, but eventually this can be performed by a computer as it's pretty fiddly work. Just as well, this is a short program then. Well, the first step is to decide what the equivalent instruction class is for each line of the program and what arguments each would take. Each assembly mnemonic is paired to one instruction class. There can be multiple mnemonics for each class, but only ever one class for any given mnemonic. First then, we'll pick out the SETAB class instructions. These need the target register and the value to load. As we can see here, that's all the load immediate LDI instructions. Next up, we'll hit the MOV-8 class. Again, there's a one-to-one relationship between mnemonic and class, and each class needs the target and destination register. Finally, we have the ALU class, which is mapped from the add, increment, and not mnemonics, effectively each operation being the argument to the ALU class instruction. So, we're halfway there. But unfortunately, the final step is the worst. We've now got to encode each of these instructions into an 8-bit instruction code. We'll start again with the SETAB class, and using the tree diagram shown at the left, we can see that the SETAB opcodes always start with a 0, 1, followed by a destination bit, 0 for A, 1 for B, then the remaining 5 bits is just a value in binary. It's just a case of writing the 8-bit opcode appropriate for what you want the computer to do. Repeat the same process for the MOV-8 instruction, again using its tree diagram, which shows we start with 2 zeros, then a 3-bit destination code, and then a 3-bit source code. Finally, we encode all the ALU class instructions, which all start with 1, 0, 0, 0, and then a destination bit, 0 for A, 1 for D, followed by 3-bit operation code as required. And there we go! Finally, I hear you cry. The full program assembled into a sequential list of computer instructions, or machine code as it's also known. These codes can now be entered into the computer one at a time and it will perform the appropriate operation that we've asked it to do. Now, as I said earlier, we have got to enter and execute these instructions one at a time for now, but when the computer gains memory, a program counter and incrementer will be able to load the whole lot into memory and let it work through them themselves. That's when it gets really interesting. Anyway, enough with all the theory, let's fire the computer up and give this program a whirl. It's demonstration time. Yay! As always, I'll start by turning the computer on. On the right, you'll see the program that we've just assembled ready to be run. If you skipped straight to this section of the video, it's a simple arithmetic sequence to evaluate 2 plus 4 plus 1, all times 3, and then -3. This allows me to demonstrate the 3 instruction classes implemented so far, SETAB, MOV-8 and ALU. Each line shows a binary opcode at the left, with the assembly language equivalent in the middle, and then any comments at the right. Now, before we get stuck into running through this program, there's a few hacks I've made to the computer to make demonstration easier. Firstly, around loading the instruction register. If I operate the control as directly, I can take a value off the front primary switches and load the register as follows. What I've done there is hold down the Select DS button to get the switches onto the data bus, then tap the Load Instruction Register button. That's a bit fiddly and I'll need to do this once for each line of the program, so instead I've hacked the Deposit Next button so that it'll automate these two actions. There's more to this than meets the eye, and what I've done is wired the switch to both the control lines but put a capacitor over the select DS line so that it's held on slightly longer than the load instruction line. This ensures that the value latches before it's removed from the bus. You can't really see what's happening with the naked eye, but without it you will get erratic behaviour where sometimes the register just won't load. The next fudge is the clock signal. At the moment the computer doesn't have a clock card, that's yet to come. So to make manual clocking possible, I've wired the clock step switch directly to the clock line. Now, that'd soon get tedious, both for me and I probably suspect you as well. So I've knocked up a clock generator on a breadboard that's stuffed into the back of the upper enclosure. You might have noticed it earlier on in this video. This generates a nice square clock wave at a steady speed using a 555 timer chip along with the usual resistors and capacitors to set the clock speed and duty cycle. I've connected this direct to the clock line and power for the clock is routed through the run stop switch. OK, great. The clock lights flash on and off in a nice steady rhythm. But note the computer isn't doing much else. Well, that's because the finite state machine on the sequencer hasn't been primed yet. I can do this by flicking the reset switch, and if I now run the clock, we get a few more signs of life. She's alive, etc, etc. OK, so a little explanation then. With the clock beating nicely, the finite state machine moves between states. Once when the clock is high, and then again when the clock is low. When it reaches the nice state, it resets because the abort 8 line is active. And this is because all the instructions implemented so far are 8 cycle. Now there's quite a lot else going on, and that's because even though the instruction register has nothing in it, that is, it's all zeros, that's the instruction for copying register A to register A, effectively clearing register A of the nothing it contained. If you rewind the video a little bit, you'll see the control lines lighting up at the right times in display A. Right, we've got everything we need now to step through this program, so let's make a start. To begin with, I'll operate the clock line by hand, but later on I'll let the clock board take over. Remember that there's no memory, no program counter and no incrementer, so I'll have to stop the clock after each instruction, enter the next stop code and then start the clock again. When those next cards are complete, we'll be able to enter the full program and let the computer churn through each line on its own. Right, anyway, off we go. So, with the first 4 instructions of the program clocked through, we can now see that register A contains the expected value of 6. Here, I've manually selected the register A onto the data bus, so it's a bit easier to see in display B. Bits 1 and 2 are lit, which in binary adds up to 6. We can now continue on with the program, and from this point, I'll let the 555 timer board take over running the clock. Following those 2 instructions, we can see that register A now contains a value of 7 as expected. Now let's move on to the multiplication. With the multiplication complete, we now have a value of 21 in register A, with bits 4, 2 and 0 set. Last step in the program then is to take 3 from the value we've accumulated so far. And there we go. The program is complete and we have the expected value of 18 in the A register as expected. I'll be focusing on creating the memory, program counter and increment cards next, so that on my next video I should be able to load the whole program into the computer and then let it run through all on its own. As always, you can find more information on my blog at relaycomputer.blogspot.co.uk, so please do take a look and I'll no doubt create another video in the future when there's something interesting to show. In the meanwhile though, please feel free to leave any questions or comments below, good or bad, as it's always nice to know that you're not talking to yourself on these things.